we go. Okay, so is everybody with me? All right, ready? Hopefully you have a calculator with you. Does everybody have a calculator? Okay, go ahead and get your calculator out. If you don't, maybe your phone has a calculator on it. If you want to use your phone, you can do that, but calculator would probably be a little better. Here's what we did last week. Last week, we read this and found out that of the relationships that exist between variables, that the simplest one's called the straight line, isn't it? And we've actually done some experiments and done some things with a straight line. Now, if you take a look down here at the bottom of this paper, what conclusion did we make about these graphs? Do you remember that? What was the conclusion? I know it was last Thursday, but what did we say about these? That's right. Every one of them was a direct relationship. Now that means as the independent variable got bigger, the dependent variable got bigger. Or what if the independent variable got smaller? Then the other one got smaller. It's like, hey, whatever you do, I do. But of the ones that are direct relationships, how many of these were called direct proportionalities? Only one. And that's the one that's linear, that goes through 0, 0. That's the only one that's a direct proportionality. This is the only one that you can say the following. If I were to make this x variable 5 times bigger, what would happen to the y variable? And we actually did that on this graph here. Take a look. If we went from 1 to 5, I just made the independent variable 5 times bigger. Well, what happened to my y value? It went from 30 to 150, and we're in the world of ratios, right? And what is the ratio of 150 over 30? 5. Wait a minute. As this got 5 times bigger, this got 5 times bigger. This is the only relationship in which you can say that. That won't work. That will not. You cannot say that here. You cannot say that here. You cannot say it here. You can't say it here or here. That's not true. The only thing you can say here is this got bigger, this got bigger. This got bigger, this got bigger. That's all I can say there. This is linear, 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 nonlinear. Nonlinear. That's all I can say. So what I'm going to do is, as far as the straight line goes, my ultimate goal, your ultimate goal, is to take a real experiment's data and turn it into a mathematical equation. And so if I had to do this one, ready? All straight lines are y equals mx plus b. Is that correct? So what's y here? You put your book up, okay? What's y? There is no y here. This is science class. It's not math. What's y? What's the variable on the y-axis? What is it?
Distance in miles.
Distance. Okay, so distance equals y equals mx. And whatever the slope of this is, as a matter of fact, that slope is going to be 30 miles per hour. If you were to find the slope of that line, it would come out to be this. And then what is the x? What's on the x-axis? Time. And what about your y-intercept?
0.
Is 0. So guess what? What you discovered is the classic distance, time, speed equation. As a matter of fact, this is distance, this is time, and the slope is speed, isn't it? And so that's where these came from. That's how they knew to write these equations like that. Okay, now that's a little review. Are you okay on that? Then what I ask you to do is, I said with, it said this had to be the dependent variable, so degrees Fahrenheit was here and degrees Celsius was here. And then what you had to do is plot the points and draw a best fit line. Did everybody do that? So what I'm going to do is I'm going to go down the row and just tell me, here's the 2 things I want to know. What did you get for slope? And what do you estimate your y-intercept as being? So tell me what you got for slope. That's going to be in a decimal number. And then what did you get for a y-intercept? Okay, ready? And if you just say, you know what, I didn't have time to do it, or whatever, just say that and I'll skip you, okay? All right, what do you have? Sarah?
Slope 1.79.
Okay.
What was the other thing?
Y-intercept is what? Just kind of estimate where it goes to the y-axis.
30.
Okay, 30. Next? Oh, you weren't here. Okay. Colleen? I'm sorry.
1.81, and then my y-intercept's like
30? 30?
I got 1.67.
1.67 and what?
32.
Okay, Eli,
1.82 and 32.
okay?
1.83 and 32.
1.68 in around 32.
Okay. That's easy for you to say. All right, yes, Kinsley,
1.81 and 30.
30, okay.
I got
1 point what?
2.1.
2.1?
Yeah.
Okay,
And then 30.
30, next,
I got 1.81 and 31.
okay?
1.82 and 32.
Okay, and you weren't here. What'd you get?
1.82, about 34.
Okay, what'd you got?
1.818,
30, okay. Now, let me ask you, eventually I'll tell you what the answer is, and then if you notice that your slope is not that close, you might want to go back and check, and here's what you might do. If you scale the axis wrong, that'll make your slope off. If you applied your points wrong, that'll make your slope off. If you don't have a best fit line, that'll make your slope off. So try to figure out what it is that makes you maybe either these, for the 1.67s, 1.68, either those are the only two people who did well, and here's another 2.1, or those three people might want to relook to see, okay, what happened here. So what happened is we end up getting a line something like this, right? And everybody put point protectors and all that, and do you think it's a best fit line? All right, now, my goal for you then is to, why do we do an experiment? We want to find the mathematical relationship between the variables, and we know it's going to be y equals mx plus b. Now, whenever I ask for that in this class, you will not put y and x. This is not math class. So what is your y variable? What is your y variable? Degrees Fahrenheit equals, that's what you're going to put here. See where it says write the mathematical equation? Degrees Fahrenheit equals m. Now some of you got, I don't know, the average is somewhere close to 1.8. Is that right? Something like that. And then what's x? Y equals mx. What's on the x-axis? And then, I don't know, a good intercept would be, what, 31, 30, 32? What do you think? 30, 32? I don't know, something like that. Now, so what we did is, you did an experiment. The data shows that this is a mathematical relationship you would get. Now, if you remember at the beginning of the year, let's see how much you remember at the beginning of the year. When we were doing temperature conversion, remember this? First, when you have Fahrenheit, first thing you do, subtract 32.5/9. Yeah. Okay, and that's that one, isn't it? What was the other one? I was interesting that the other class had trouble. They were struggling to remember the other one. What do you have?
9/5.
What do you multiply it by? I mean, what, to get Fahrenheit, what do you do? So use 9/5 instead of 5/9, so times what? Okay. And then what? Oh, uh-oh. Now, so you might be thinking, you got it wrong. Really? What's 9/5? 1.8. What's 9/5? 1.8. Oh, whoa, that's where that came from. It is. They didn't really care. When they were doing the Celsius temperature scale, they didn't care about Fahrenheit. But later somebody said, but what if I wanted to convert? What is the mathematical relationship between the two? And they probably did something like this. And all of a sudden they found the equation. I think some of you think the equation was always found in the science book. What about before that book was written? Another science book. What about before that was written? Where do you think these equations come from? Experiments. They come from experiments. And so, and the more times you do this, you'll get a number very close. They probably thought, hey, that's really close to 9/5 and 5/9, that kind of thing. You get it? Matter of fact, your book, your chemistry book, doesn't even show 9/5 and 9/5. They actually say 1.8, and you know what 5/9 is? 0.555, isn't that right? Something like that. So some chemistry books, they don't even mess around. They just say, memorize it. Just memorize it. Remember, it's 1.8, 0.558. I like the 5 ninths, 9 fifths myself, but. All right, what do you think so far? Okay, so that one is, how would you classify this, all right? What words could you use to describe this relationship? Ready? What could you, help me classify it? Is it a direct relationship, or is it inverse? If X gets bigger, does Y get bigger?
Yeah.
Then it's direct. So we know it's a direct relationship. Is it direct proportionality? What else can you say? One more word. Linear. It's a linear, and it's a direct relationship, but it's not a direct proportionality. So how do you know? First of all, there's no way it's coming close to going through 0, 0. Is that right? Here's another thing is, let's try this. If it was a direct proportionality, what would happen if you made this 7 times bigger? If you made this 7 times bigger, then what would this do? If it were direct proportionality, what would be happening? 7 times bigger, 7 times bigger. Well, 7 times 50 is 350. All right, there's no way this is a direct proportionality, is it? Not even close. It is a direct relationship, and it is linear. What do you think? You okay on that? All right, we're getting into the big boy growth stuff now. Ready? Let's turn the page. Now, if you'll stay with me today, I am going to talk a lot about numbers, and I'm not talking about math class. I'm just talking about numbers. You get it? And the human mind, God made your mind that you can do things with numbers. You can even use your calculator to help you, okay? But I want your mind to play around with numbers today. And if you do, you'll see a pattern. And I will show you, even if you don't see the pattern today, by tomorrow, by the end of tomorrow, you're going to see a pattern. And you're going to say, that pattern is very strong. I didn't know that. No one ever taught this to me either. I wish they had. Okay, now, I'm going to read here. When analyzing quantitative data, and I said, what? Do I remember what that word means? One is often interested in discovering the exact mathematical expression that shows how one quantity varies with another, while all other quantities are held constant. Here's one of my goals. One of my goals for you is that after we're done with this lesson, you will create a lab. You and your partners will design a lab so that only the 2 variables that you allow to change, the independent are going to be allowed to change. You will decide how to get the data. You will make sure you zero your equipment. You'll do everything. And then you're going to get a graph. You're going to get data, and you're going to graph it. You're going to say, what does this mean? What does this graph mean? How do I interpret the graph? And that's what this unit is called, graphic interpretation of data. And I think you'll get an idea of how a real experiment works and how they eventually turn it into a mathematical equation. All right. And by the way, all the other variables have to be held constant, don't they, to get a controlled experiment. There are several ways of discovering what that relationship is, if it exists. One of the most useful methods is a graphic interpretation of data. To get an idea how this method is applied, we'll investigate a few of the more common relationships. Fortunately, many physical quantities, that's physics, are related in one of 6 ways. So eventually, you're going to have to be experts on all 6 of these. You're not going to be an expert today. Now, another thing is, just like people stop saying, I don't like saying deoxyribonucleic acid over and over and again. It's better if I want to write some notes, for example. I'm going to use abbreviations for this. If I want to show you, if I say something is a direct proportionality, I'll probably say DP, direct proportionality. Let's skip down to another one. This is a direct proportionality to the square, also known as a direct square proportionality. Okay, let's skip down 2 more. Direct proportionality to the square root, that's a direct square root proportionality. Everything might be in here or there or in the
Sorry.
in the drying racks. Tell me what you want.
Clear rulers.
Okay, back there, I have a bunch of rulers in the ruler stand. You can take the whole thing.
Sorry, everybody.
You can take the whole thing. That's fine. They like seeing you.
We're making Jessica fit more. And everybody goes, yay. Woo.
What was I saying? Oh, yeah. Okay, so now, so those are my abbreviations I'm going to use, and you might want to use abbreviations because when you eventually get tested on this, you might want to label a graph. That's a direct proportionality, DP. Let's go to the next one. Inverse or indirect, same thing. Inverse proportionality, inverse square proportionality, and inverse square root proportionality. Now, don't get scared. We're going to go through each one of these, and if I can show you the pattern, you're going to understand it, okay? All right, let's go down here. Next paragraph. See if you can understand this paragraph, okay? I'm going to read it, and it's Monday morning. See if you can still understand it. Right? In considering each of these relationships, if actual experimental data were used, there might be considerable scattering of the plotted points due to experimental error in the data. Although this would be realistic, it would obscure the underlying relationship between the variables. Hence, the common relationships are illustrated with idealized data. Therefore, there is no experimental error in this data, which is not real data in the usual sense. All right, what do you think? If you understand over 90% of what I said, raise your hand. All right, how about more than 80%? How about less than 50%? I'm okay with that. I'm okay with that. Okay, now I'm going to interpret, okay? I'm going to translate. It says, when considering each of these relationships, see these six? It says, if actual data were used, there might be considerable scattering. And what they're talking about is maybe scattering might mean that the data points are not really on the line. They're like, remember that? Isn't that called a scatter plot? Okay, so anyway, they might not be there. And that's fine because that's like real data. That happens all the time with real data. But you know what we're going to do for this packet? For this packet, guess what kind of data I'm going to use? Idealized data. What's that? Near perfect. A little bit of rounding errors, but near perfect data. And so guess what? Now you will know it really falls in that line. And because I'm not really trying to teach you how to draw a best line, I want you to say, what is the relationship between it? So we're not going to use real data. We're going to use made up data. You get that? That's what they're trying to say. Okay, so the good news for you, and I don't know if they're going to start doing these SAT and SAT, SSAT, ACT tests. I don't know if they're going to do it again, but if you do the ACT part and they have the science part, they always have data tables, always. And if you can quickly figure out who the independent dependent variable is, you can be able to look at a data table and do what most people can't do. You'll be able to try to interpret it before they will. So here's what we're going to do, right? And guess what kind of data they use there, because they don't want people criticizing their test. So they're going to use almost perfect data. You get that? Because they don't want somebody coming back, well, I missed a question because that wasn't on the line. You know, they don't want anybody challenging their questions. See that? So they'll probably use near perfect data. All right, so here we go. It says here, we already did direct proportionality. It says, how is the length L related to the width of any rectangle of 60 square centimeters of area? This shows the length L plotted against the W. Since the graph line is a curve rather than a straight line, the length cannot be directly proportional to width. Is that right? If it was directly proportional, wouldn't it have to be linear? This can't be. It can't be. Now, I used to do this when I had a little bit more time. I used to have a homework assignment. You get some graph paper. I said, go home and make 10 different rectangles. They all had to have one thing in common, though. They had to have an area of 60 squares, 60 square centimeters. And people would come in, they'd have their rectangles numbered. And what it's doing is generating data. So let's take a look. Look right here. And the first thing I'm going to ask you to do is, which one of these do you think was the independent variable? Which one was the independent variable? And that's my big question mark. So I want you to always start with this. Which one of these was the independent variable in this experiment? So everybody think about it. We're going to take a vote. You have to raise your hand. You have to raise your hand. How many people say that length is the independent variable? Raise your hand. I can't believe it. Only one person? All right. How many people say width?
Yeah.
All right. Why do you say width? Let's see. Walker, you said width. You like? It's 'cause your last name starts with a W. And you have a bias for W things.
Oh, that's it.
What?
I gotta go.
What?
I don't know.
Just guess.
It's an educated guess. You have a feeling, didn't you?
Feeling? A feeling's an educated guess.
Yes.
Okay. What do you think? What do you got?
I said width because the width measurements are going up by whole numbers and there are no decimals.
Okay, I'm gonna agree with you. In this case, if I wasn't here to do this experiment, if it wasn't my experiment, okay, then I have to think about this, and this looks very human-y. Doesn't it look very human-y? And 1, 2, 3, 4, 5. I think a human manipulated that one. That's number one clue. Number two clue, it says here, I look at the graph, and where do you put the independent variable? On the x-axis. Now, you got to be careful about this because the independent variable is on the x-axis, but guess what math does all the time? Even since middle school math, if you had x and y, who was on the left? X was on the left, and y, not here. And you can't fall into that trap and say, well, x is always on the left and y is on the right in math, so if I look at somebody's experiment, that must be the independent variable. That must be, no, you can't do that. You have to either know something about the experiment or get a clue from this. And so what I want to do is, step number one, find out which one is the independent variable. You got that? So I did that. Next, as the independent variable got bigger, as width got bigger, what happens to length?
It got small.
Okay, so that, number two, so number one, find the independent variable. Number two, find out if it's direct or inverse. Is it direct or indirect? Indirect. And that's the same as inverse. I like inverse better. So I know it's I know who the independent variable is. I know it's some kind of an inverse relationship. Now, which one is it? And we're going to try to find out. So what I'm going to do here is I'm going to do something that a real scientist probably wouldn't do, but you could do it on an ACT test. If you have really good data, and your data is really close to the best fit line, you can try this. But I'm going to play this thing called a numbers game. Now, I always start with independent variable, and I want to be nice to myself, so I'm going to go from 1 to 4. Now, ask yourself, in the world of ratios, how many times bigger did I make that number? Everybody in the room should say it. How many times bigger did it go?
It got 4 times.
About 4, okay. So it got 4 times bigger. Now, what happened at the same time? This used to be 1, and this used to be 60. By moving 1 to 40, what happened to this variable? How did the responding variable, the dependent variable, how did it respond? And in the world of ratios, 60 over 15, that's why you have a calculator. What do you get? 4 times what? Let's try it again. Let's go from 1 all the way to 9. Let's go from 1 all the way to 9. How many times bigger did the independent variable get? 9 times bigger. All right, use your calculator and tell me what happened over here. 60 divided by 6.7. Let's try it. What do you get? Pretty close to 9. Okay, so this got 9. See, oh, look at that. So guess what? Just like in the world of direct proportionalities, in the direct proportionality, if you get 4 times bigger, I get 4 times bigger. If you get 9 times bigger, I get 9 times bigger. But what about the inverse proportionality? What's the pattern? What's the pattern? The independent variable gets 4 times bigger. The dependent gets 4 times smaller. See? 9 times bigger, 9 times smaller. Do you see the pattern? Okay, so this is called an inverse proportionality. So I'm going to declare this one to be an inverse proportionality. Now, when I eventually test you on this, it might not be till Monday, but because I don't think we can quite get done this week. But I have a whole page, and all it is data tables. And then the questions underneath there is about 12 questions. It'll say, which graph, A, B, C, D, E, F, which graph shows an inverse proportionality? You say, what? How am I supposed to know that? Well, you go to each graph, analyze it real quickly, play a numbers game, and put a little abbreviation on it. You said, I got it. I got all of them. Okay? I have another page, though. Guess what's on another page? Only graphs. Only graphs. So now, let's pretend that you look at this and said, what do you think? Is that direct? Is that one of the directs? It can't be. As this gets bigger, this gets smaller. It can't be any of the directs, is it? It must be one of the inverses. How in the world am I supposed to know which inverse is it? Is it this one? Is it this one? Is it this one? How do I know? So we're going to play this thing called the numbers game on the graph. Let's try it. Now, be careful when you do this. Be careful when you get your points. That point is 160. Now I have my X and Y value, don't I? Let's do another one. Let's go down here to 4. Let's go to, I don't care. We go to 4. 4, about halfway. 415. Okay, now, watch. When you're going to play the numbers game on a graph, and again, in a real experiment, you might not want to do this because your data might have too much error. But on close, really good data, which one do I start with, X or Y? Same thing I did up here. What do you start with? X or Y? That's a good, you had a 50-50 chance. You always start with the independent variable. Which one is that? No, X. X is the independent variable, isn't it? So we're going to start with X. Right. X went from 1 to 4. What happened? What did you do to the X-axis?
4 times.
You get 4 times bigger. 4 over 1, right? Now, what happened to the Y-axis? That's right.
Let's go beam.
Ding, ding, ding.
Dude.
I have confirmed this is an inverse proportionality. All right, what do you think? It's kind of fun when you don't say it's math class and you just kind of play with the numbers a little bit. You said, I'm feeling a little smarter here. This is kind of making sense to me. Okay, now, I would like to show you though, because there is error in a real experiment, and I would like to see how a real scientist does this. They probably don't play the numbers game on the data table or the graph because their data, it could be some of the points are way off of the line. So how do they do it? And I'm going to turn the page, and this will be the one part, this will be the hardest part of the lesson today, all right? Now, take a look here, and you should recognize this and this. Where have you seen that before? That's the same data table that was on the other page, isn't it? Yeah. Now, eventually, I am going to have you guys go away from hand-drawn graphs, and we're going to have these laptops out, and these laptops have a program on them called Logger Pro. Logger Pro is one, even colleges use Logger Pro, and the laptop has this program on it, and if you put your data in there, it will make a data table for you. It will actually graph your data, and it'll even find the slope. If it's a straight line, it'll find the slope for you. It'll even tell you little statistics and show you what's the likelihood that your data shows a pattern. Okay, it's called an R value, and that's a statistics term. Now, here's another thing that they will do is, what I'd like to teach you is when you get a nonlinear graph, you have to straighten it out. Now, I'm going to show you how this is the hardest thing I'm going to say today, okay? Just stay with me. Stay with me. Now, guess what they did here? On that computer program, when you do this, and you have a graph kind of like this on one of your experiments, you'll say, new calculated column. And what it'll do, it'll say, what do you want to do? You'll say, I want to have w to the minus 1 power. What does that mean? What is x to the minus 1 equal? We talked about this before, right? Isn't it that? Doesn't it give you the inverse, the reciprocal? Everybody get that? So when you tell that calculator, now right now you're doing it by hand. So if I ask you to make this column, you'd go 1 over 1, 1. 2 over 1, 1 over 2, sorry, 1 over 2, 0.1, 1 over 3, 1 over 4, and you would do this on your own calculator. Get that? And you might say, what are you doing? Why are you doing this? You already had your 2 data tables. You had your 2 columns. Why are you making a new one? And I want to show you something. This is pretty neat. This I think is really neat. Look at the graph. This graph is not length and width anymore. It's length and 1 over W. Do you see what's happening? Now, stay with me. This is the best part. You know what this graph proves? This graph proves that length is directly proportional to, not W, 1 over W. Look, isn't that right? Look, L is directly proportional to what? 1 over W. Now, if you have proved that, multiply both sides by W, tell me what you get. Multiply both sides by W, what do you get? Is that right? So here we go again. Watch now. If you can prove to me that length is directly proportional to 1 over W, then you have proven to me that L and W are inversely proportional to each other. Remember inverse proportionality? Don't they both on the same side of the equal sign? And guess what I can do with a straight line that I couldn't do with a curved line before? What could I do to a straight line that I couldn't do with a curved line? Oh, I lost you on that one. Yes. Okay. How many slopes does a straight line have? 1. How many slopes does this curved line have? Infinite. There's a slope here, there's a slope here, there's a slope here, there's a slope here, there's a slope here. It's infinite. A curved line has an infinite number of slopes. There's no way you can find a constant on a curved line like that. But guess what I can do now? Now, I can say L times W equals whatever the slope of that line is. The slope of that line is going to be my constant. Now, can I tell you that the other class, which is a little bit higher than you in math, they're taking statistics and everything, no, it took almost a whole minute. It took a whole minute. Oh, sorry. It took a whole minute before they could figure out what this was. I'm asking you right now, what do you think the slope of this line is going to come out to be? And you might as well take a guess. I heard a whole bunch of guesses last period. It took a whole minute before somebody got the right answer. What's the slope of this line going to be? What? Raise your hand. Just take a guess. I heard about 10 guesses last period. Yes? Say it again. You know why you said that? Because in math, they always label the x and y the same. And when you get a 45-degree angle, the slope is 1. And somebody taught you that. Good math teacher. But no. You know what? The scales aren't the same, so it can't be 1. What do you got?
5.
How much?
5.
No, I don't think so. What is it?
6.
I don't think so.
Oh! AP statistics over here. I am
Wait a minute, wait. Can I tell you what happened? You forgot that this is times 10 to the minus 1.
50.
What?
1/6.
What?
1/6.
No.
150.
No. No. Wait, you're going the wrong way. All right. Wait, what?
60.
Somebody said it.
60.
Who said 60?
Walker. Me and Walker said.
All right. Hey, you know what? Hey, wait. Can I tell you something? You forgot the original experiment. The experiment says, make me a bunch of rectangles, and they had one thing in common. What did the one thing they have in common? They all had an area of 60 square centimeters. Remember that? And in math books, they say length times width equals area. Oh, wait. Look. Length times width is area, and all of them had the same area. Area was held constant. And it was 60. Wow. Now, I can actually prove, like a scientist does, I can prove that L is directly proportional to 1 over W. Another way of saying that, L and W are inversely proportional to each other, and now I can find the slope. And I turn my experiment into an equation. Yes, by doing it with rectangles, and they all had the same area, maybe it makes more sense now. But you might do an experiment in here, you have no idea what the real answer is, and it might come out like this, and you said, these are inversely proportional to each other. And here's your constant right there. All right, with me? Okay, now what I'd like you to do is, don't do it yet, I'm gonna have you get in small groups, and here's what I want you to do. I want you to figure out who the independent variable is on the next experiment. So you're gonna read this, who's the independent variable, and what you're gonna do is, you're gonna figure out was it direct or indirect, and you're going to play the numbers game on the data table, play the numbers game on the graph, and without turning the page over, don't turn the page over, I want you to know this is called a secondary graph. What is the secondary graph going to have here and here that'll produce a straight line? All right, that's a lot to ask for, but let's go ahead, sit in your small, yes? I can't hear you.
Because if the line hits 0, 0, and line hits 6 to 10,
Yeah.
then it should be 6, right?
No, Eli.
Because if you do the
Well,
formula, you get 0 minus 60, and then you get 60 over 10.
No, but
which is
60
But then
over 1 is
Eli,
60.
negative 1. You go to the negative 1.
The line is a negative 1.
These, the way they did this, this is actually 0.2, 0.4, 0.6,
Oh, well, it doesn't say
and that's why you say times 10 to the minus 1.
I see.
So you know what? Hey, you know what? You're right. You know what would have been just as easy? They could have been just as easy to put 0.2, 0.4, 0.6.
I don't see why they wouldn't do that.
It's okay, Eli.
Okay, let's go.
Because it makes less sense than it needs to? Yes.
Get in little small groups. Get in small groups.
Finn, come here.
Eli, you can go to the company that made this and complain.
It's unnecessarily realizing me and Karen
I wish I could. Whoever made this map is stupid and doesn't deserve their PhD. Yeah, they should be fired.
Eli, that's funny. You think the person who made this